In this video, I'm going to rigorously show the connection between a function's derivative and whether or not the function's increasing or decreasing on an interval. And I mean, I would file this video maybe under an optional, for your own interest, because I don't think it's crucial. I think that most students pick this up pretty easily, but it is a subtle distinction, and I think it's important to get some exposure to a rigorous proof if you're at the high school level. And so this is what we're trying to show, this corollary here, that if f is a function that's continuous on a closed interval and differentiable on the open interval, then its derivative being positive at each point on that interval means that it's increasing on that closed interval. And if the derivative is negative at each point, then f is decreasing on that interval. So the question I want to answer here is why, and this will also give you some exposure to what a proof might look like in calculus if your teacher hasn't been doing that. So remember the definition of increasing and decreasing. We're going to need those. To do this proof, let's start with the fact that we're going to assume we're just going to pick two x values on our interval a to b, and let's just let's say pick x1 and x2, on my closed interval a to b, and let's just assume that x1 is less than x2. So that means that if I subtract x1 from both sides, that means that x2 minus x1 is positive. All right, so we'll just keep that in mind. All right, now here's where I said that the mean value theorem makes this connection. Here's where the mean value theorem comes in. By the mean value theorem, we know f prime of c equals the average rate of change over that interval x1 to x2 that I just introduced. Okay, that for some c on the interval x1 to x2. All right, so that's where the mean value theorem comes into play. So now what we're going to do is we're going to multiply both sides by x2 minus x1. I'm going to shrink this down a little bit. I guess that cloud is now circling nothing. Okay, so that means that if I multiply both sides by x2 minus x1, then I get this relationship. Now, here's where we start noticing what's positive and what's negative. Because remember, my goal really is to show, I'm trying to show that f either increases or decreases depending on the sign of the derivative. So I need this relationship if my function's increasing, and I need the one below that if it's decreasing. So we're trying to find out something about f of x2 as it relates to f of x1. So let's just assume, let's do the first part here in blue. Let's assume that if f prime is bigger than 0, well, that means that that's positive. We already know that x2 minus x1 is positive because I situated the points that way, which means that a positive times a positive is a positive, and f of x2 minus f of x1 must be positive, therefore. So that must be positive. So that means that f of x2 minus f of x1 is bigger than 0, and that means that if I add f of x1 to both sides, f of x2 is bigger than f of x1. But of course that means that just means that f of x is increasing on the interval a to b. So on the other hand, let's start with the same relationship. Let's say, I've got f prime of c times x2 minus x1 is equal to f of x2 minus f of x1. Well, if we assume, so this time I'm going to prove what I just circled in black, let's assume f prime is less than 0. Well, then that means that's a negative. We situated it so that that's a positive. A negative times a positive must make this a negative. So that's a negative number, so that means that f of x2 minus f of x1 is less than 0, which means that f of x2 is less than f of x1, and therefore f is decreasing. On the interval a to b. So, I mean, I wouldn't say this is anything worth memorizing at all. Just the point of it really is to show that the mean value theorem is really what's making the connection between a function's derivative and whether or not it's increasing or decreasing. And I think that's really the take-home point, the take-home message here, that I'm sure is overlooked in most calculus courses. So, anyway, in the next video, I think we'll look more at things that are more relevant to probably AP Calculus students, but this is a video just for your own interest if you like to see proofs.